Good morning, everyone, and thank you for helping me get up so early. Greetings from the future. It is 4 a.m. on Friday, February 19 here. I am Fernando Beltran from Auckland, New Zealand. This paper, I will do an assessment of two FCC auctions, it's auction 102 and auction 105, which sold the spectrum for the deployment of mainly 5G services. I used the bidding history of some selected bidders in each auction to assess individually the degree to which the data conforms to known definition of rational bidding based on a revealed preference. I used Fred's theorem to approach the issue of auction efficiency. So what is this talk about? I used Churchy et al. 2014 paper to test the consistency of bidding using revealed preference theory for some selected bidders in the auctions. In variant 2006, we find a thorough recount of revealed preference. The paper characterizes the generalized axiom of revealed preference, or GARP, and does the same for the homothetic axiom of revealed preference, or HARP. It reveals how GARP is related to the existence of a utility function, rediscovering seminal work by Afriat. Also in a 2019 paper, Heffer and Schrestrand extend the applicability of GARP and HARP by introducing efficiency indices to test relaxations to these actions. I use Afriat's theorem and the indices to reach some conclusions. Since 2018, the FCC has auctioned a spectrum aimed for 5G services in the 28, 24, and 3.5 gigahertz bands. Auction 101 raised 700 million, while auction 102 generated 2 billion. Auction 102 sold two 100 megahertz blocks in the lower 24 gigahertz and 5 100 megahertz blocks in the upper portion of the band. Last year, in July, the long-expected CBRS auction offered 22,600 licenses and in over 3,200 counties across the US in the 3.55 to 3.65 gigahertz band. The auction raised over 4 billion. This paper analyzes bidding happening in auctions 102 and 105. Now a bit of a background on the main concepts used in the models. The auctions are standard clock auctions. The auction proceeds in rounds offering multiple licenses in M areas. At each round, the auctioneer announces a clock price vector and each bidder responds with a demand vector. The collection of these demands vectors over all rounds is the bidder's demand history. Each bid is constrained by an activity rule, which in Osobel and Baranov's words is a constraint on the bids that a bidder is permitted to submit in a given round of a dynamic auction as a function of the bidder's prior bidding history. We call V the value function that characterizes the bidder's preferences. The activity rule constrains a bidder's bids to be in a feasible set for each round. Now, if for every round T, the demand vector is such that it maximizes a bidder's utility function, just like shown here, we say the bidder bids straightforwardly according to its value function. All right. So activity rules are important to this discussion because they are the main mechanism the auctioneer used in auction 102 and 105 to promote active bidding while discouraging bidding strategies that may be detrimental to the auction objectives. An activity rule defines the set of feasible bids. The activity rules in these auctions are point monotonic. They are rather simple. One unit or license in each service area is given a number of points. The eligibility of a demand vector Z is the product of Z and the vector of eligibility points. So a point monotonic activity rule is such that the feasible set of bits in any round, like T, is the demand vectors for which their eligibility is no greater than the eligibility of the bit in round T minus 1, that is the previous round. Ausubel and Baranov exhibit three properties that an activity rule should ideally follow. They call them axioms. So axiom 1, the activity rule should allow bidders to switch only to bundles that have become relatively less expensive, and this would make parking strategies as impractical as possible. Second, it should allow straightforward bidding. Third, the feasible set of at round T must include at least one of the bundles demanded in previous rounds, so there's no dead ends. Point monotonic rules satisfy axiom 3, but generally are inconsistent with axioms 1 and 2. Let's turn now to reveal preference. We start with the set of observed price quantity decision pairs called S. These are the observed data. Now we build a relation between demand bundles. We say that a demand bundle QI is directly reveal preferred to bundle QJ if is the best at price PI. Next, we find all couples QI, QJ for which the above condition is consistent. We refer that as QI R, QJ. That basically R is known as the transitive closure of directly revealed preference. So it is a consistent in a transitive way. In other words, we build the transitive closure of the revealed preference introduced above. With these settings, what do the generalized axiom of revealed preference and the homothetic axiom of revealed preference tell us? But let me provide some intuition first. Variant came up with two brilliant questions that help us understand GARP and HARP. In motivating GARP, Variant asks, when is the observed behavior consistent with utility maximization? And for HARP, Variant asks, when is the observed behavior consistent with maximizing a utility function of a particular form? That would be a homothetic function. So let's take a look at a small example. On the first table, you can see two matrices, one with quantities demanded over 4 rounds on 3 products and or service areas, and with corresponding prices on the left-hand side. Below, you see the product of the two matrices. Now, matrix R sub 0 on the top is a binary matrix that describes the preferences revealed by the data, which are also shown on the graphic. And matrix R is the transitive closure of the revealed preferences. So see how the graphic is completed, showing the revealed preference and the relation R. Now, let me torture you with some formality. Formally, GARP says that when a bundle QI is preferred to bundle QJ in the sense of transitive closure of the revealed preference, then QJ cannot be strictly directly revealed preferred to QI. So the transitivity doesn't break. HARP is a more technical condition. This is a condition that ensures the existence of homothetic utility function. It states that the sum of the logarithms of price quantity products, as you can see, for any sequence of any size of the set of observations cannot be negative. Notice the sequence is any subset of the set of observed data. If we test a data set for HARP or GARP, the results are a pass or no pass. So these tests are unambiguous. Each condition is met or not by the data. So it is a good idea to relax the condition and be less demanding. You can see we can relax the definitions by using numbers EI to EN, which numbers between 0 and 1, which render the inequalities less stringent. And obviously new definitions in which we are using the numbers introduced. So why would we do that? Well, before going there, let me just show you for the example how GARP is violated. Basically, we have that the definition of GARP doesn't apply. So there's an exception here for the relation between 4 and 2. And when that happens, GARP is violated. So it suffices 1. That's the idea behind the relaxation we want to introduce. So how to test GARP and HARP? Let's see. So far we have defined GARP and HARP, learned that they are unambiguous tests, and introduce a less stringent condition for each condition based on a parameter for each observation. We want to use the less stringent condition definitions to build new related tests. Following Churchy, we built a graph G, and the graph is basically a node for each observation. Each pair, ij, defines an arc when the parameter ei is greater than the product pi qj, and the length of the arc is the difference of the two terms. So using the graph, Churchy shows that a set of observed data satisfies GARP of E if and only if the graph so defined does not contain any cycles of negative length. And for HARP, we define another graph where the length of the arc is logarithm of the product minus logarithm of the parameter. Testing HARP means that a data set satisfies HARP of E as a function of E if and only if the graph does not contain any cycles of negative length. So let me explore a particular case by making each of the parameters equals to a common value E. We're looking for a value of E that makes the data set pass the relaxed condition GARP E. This is the Auckland efficiency index, AEI, is that value, that maximum value. Likewise, for HARP, the homothetic efficiency index is such a maximum value, E star. The latter means that data set satisfies HARP of E star. These are the indices we used on the data sets produced by auctions 102 and 105. In various words, GARP is equivalent to what Auckland called cyclical consistency. But Auckland went farther. Auckland's theorem states that a set of observed data satisfying GARP is equivalent to the existence of a utility function that rationalizes the data in the sense that utility is maximized. So let's take a look at the algorithm that is used to get the results. So Auckland's theorem and the test introduced above show us that the way to express how consistent the observed data or billing history are, as indicated by the computed maximum value E star. You can now see the algorithm used to calculate E star for GARP, and there's a similar algorithm for HARP. First, prices are normalized, so basically all products are set to 1. Next, we obtain all values of products PI, QJ normalized for those products which are less than 1. and sort them in ascending order. Then we look at the median value in list A and test GARP for the median, that is GARP of X. Values above X or below X are removed depending on GARP X is satisfied or not. We end up with the closest PIQJ to this south number E star, and that's good enough. So we did it for auctions 102, auction 105. We have some results, some incomplete table of values that are not yet verified, so I can present some of them. But for auction 102 selected bidders, we have the value of the indexes. So the closest to one, more consistent, the bidding is with a maximizing utility. We see an exception in US Cellular, and on the auction 105, we have another exception, at least for that small set of bidders, for 0.22 for cable one. So what we read from the tables is that bidders were bidding in a rational way and were maximizing their utility at every step. We would like to compare this quickly with the same approach for that I've done in the past for auctions in Canada. These auctions use the combinatorial clock auction, so it was not the same format as in the US. And we have a whole bunch of operators that participated in sometimes in all those auctions, sometimes in only one, sometimes in two of the auctions. You can see the same indexes calculated here, especially under AEI. You see how they are becoming more to conform with rationality and the maximization, no violations of GARP. But that has an explanation as well. That 600 megahertz auction included a GARP-like activity rule as well. So it was constraining more in that sense, in the sense of GARP, but again, a activity rule that complies with the three axioms stated by Baranov and Ausubel. So in conclusion, major bidders in auction 102 bid consistently according to GARP. And probably this is the most important observation. Following Afriad's result, auction 102 exhibited a high degree of efficiency as the Afriad indexes for such bidders remained close to 1. So this is the main point. If bidders were bidding in a consistent way according to maximizing the utility, then one would expect the auction being efficient, as most of the bidders are bidding that way. There's no evidence of homothetic preferences for some of those major bidders. You could remember from the tables that the values of homothetic index are low in many cases. Although auction design allowed bidders to decrease their demand as rounds proceeded, this was rarely the case. Auction 105 exhibits similar results. Cable 1's case is interesting because its index is rather unusual. And it would be a matter of looking further into the data, which I haven't done right now. So thank you. That's the end of it.